All right, in this video we describe the Newton-Raphson method for solving nonlinear equations. This is the same equation that we solved with the bisection method, f of x equal to 0. The advantage of Newton-Raphson method is it converges much more quickly. Also, you do not need two initial guesses, only one initial point. The drawback is if your initial guess is too bad, then the Newton-Raphson method will not converge. And that's what he says here. He calls it an open method. It does not converge if your initial guess is not close enough to the root. Right? The derivation of Newton-Raphson really depends on this picture. Suppose my initial guess is here at xi. Okay. Let me get my drawing pad. And then if xi is there, then f of xi is going to be here. Well, we want to find a value of x that's closer to the root. Well, if you know the derivative at this point, the derivative is the slope of the secant line, slope of the tangent line. That's f prime of xi is the slope. Okay. And I want to find this point here such that the tangent line intersects the x-axis at this point. And you can see if I do that, then I should get a point x which is closer to the root. All right? So how am I going to find this point? Again, this point is the place where the tangent line to the curve at this point intersects the x-axis. Well, we have a triangle here. This height is f of xi. Okay? This angle, you call that theta. This length here, I'll call this delta x. Now notice that f of xi over delta x is equal to the slope of this line. So we have f of xi over delta x is equal to f prime of xi. Okay, I can do this to solve for delta x. Delta x is equal to f prime of xi. I'm sorry, it's equal to f of xi. Let's go back. F of xi divided by f prime of xi. Now delta x is exactly the distance I need to move from my current estimate of the root to my improved estimate of the root. So what does that tell me? My new estimate, xi plus 1, will be equal to my previous estimate, xi, minus delta x. But delta x is given by that formula. So xi plus 1 is equal to xi minus f of xi over f prime of xi. All right, very simple equation. We just need to implement this equation on our spreadsheet. Okay, well, I'm going to do something a little bit different this time. We've already have a spreadsheet for the bisection method, and this method is quite similar to the bisection method. So what I'm going to do is go to my bisection method spreadsheet and modify it to give a Newton's method spreadsheet. And here we go. And let's go ahead and open up my bisection method spreadsheet. And it's right here. All right, so I'm going to modify this. Let me get rid of the graph because I'm going to have to make a new graph. And this is going to be Newton method for finding roots. Okay. Now, let me cut and paste the equation that I'm going to need in order to do this. All right, for that I need to go back here And here we go. It's right here. So let me paste it. And we'll put that in my spreadsheet right here. So that will help me remember. All right. Let me put it down here. Don't need it quite so big. There we go. All right. Now, I still have a function to evaluate. What I need here also is the derivative of the function. So let me do the same function here, cosine x. I'll look for the same root using this different method. So my function will be cosine of x. I'm going to need the derivative. Now we know the derivative f prime of x. We know from calculus the derivative of cosine is minus sine of x. Okay. Now this has messed up all my equations. That's okay. I'm going to have to change some of these anyway. So that's not a problem. Now instead of upper x, what I want is the initial guess. And I'll make my initial guess be 2, just like before. And I'll also want my actual root in order to verify the accuracy of my method. Okay. All right, so here we have iteration number. And we're going to have to change a bunch of stuff here. Let me work out my column headings first. First of all, I'm going to need a column for xi. To compute xi plus 1, well, actually, xi plus 1 is going to go in the space below. So I don't need a place for xi plus 1. I do need a place for f of xi. Now notice I've got that ready-made over here. I had xl here. So this could be f of xi right here. And I'm also going to need a f prime of xi. So I'll make that here, f prime of xi. And it always tries to make that f capital. Let's see if I can make that small again. So all I need in this algorithm is this column, and this column. Let me get rid of all the other columns I don't need. I don't need these two columns. So I'm going to select this part, right-click in this area with the right mouse, delete. It will ask me if I want to shift up or left. I want to move the columns over, so I'm going to shift left. All right. Now, as I said, I only need 1, 2, 3 columns. I don't need this last blue column, so I'm going to get rid of that also. Another way to delete is go Edit, Delete Cells, Shift Cells Left. All right. So let me fill in what I want to put here. Xi at the beginning is going to be my first initial guess. F of xi, well, notice that it's already correct. So I don't need to change that. F prime of xi, it's not going to be cosine anymore. It's going to be minus sine of this value. Okay. All right, now what goes in the next line? My next estimate of x is going to be found using this formula. Xi minus fxi over x prime xi. I have all of these in the previous row. So this equals xi minus parenthesis f of xi divided by f prime of xi. All right, take a look at that equation again. Okay. Make it a little bigger. Okay. That's the equation I put in for the new estimate of xi. Okay. Now f of xi, that equation's correct already. The equation that goes here is f prime of my new xi. I can just take this equation and fill down. Edit, fill down. Okay. All right, notice what's happened here. At 2, f of 2 is minus 0.4. F of this value is 0.02. That means that since f of this value of x is very small, that means this value is very close to the root. Now I've done my equations in general, and all I need to do is fill down this entire line. Edit, fill down. Okay. Notice that we now have extremely small errors after only 3 iterations. I'm going to save this file as Newton. And I've already saved the bisection. I'm going to save this as Newton in English. Okay. And let's compare, just for a moment, let's compare this with the bisection method. If you notice in the bisection method, this is my estimate here. It took me 6 iterations to get down to 1.570. Actually, it didn't get back down to 1.570 until here, until 10 iterations. That's when my approximation is accurate to 4 decimal places. How long did it take to do the same thing in my Newton method? Well, let's go and see. 4 decimal places after 2 iterations. Incredible difference. Much faster convergence. But note the cost. The cost is that I need to know the derivative of the function. Sometimes you have a very complicated function where the derivative is not known. In such cases, you cannot use this method. Okay. All right, let's do an error analysis. Let me leave max error for a minute. Let's do actual error. The actual error here is going to be equal to the difference between my estimated root and the value that I happen to know. So that's going to be the absolute value of, this was my actual value here, minus my estimated root. Oh, sorry, my estimated root is here. Okay. Let me bring that over to make it more clear. You see, my actual root, I'm sorry. You can see my formula here. Okay, and let me fill down. And you can see that the value is essentially 0. Oh, I'm sorry. Made a mistake again. I need to fix the reference, which I didn't do. Let's do it again. Click here. I always want to have B6, so I want B6 to be a fixed reference. Click in here, Shift F4, Enter, and let's go ahead and do my fill down. Edit, fill down. Right. All right, now you can see still that the errors are extremely small. Right? Instead of maximum error, well, I'm going to do theoretical error based on the document back here. Here we have an expression for relative error. Let me copy this too. And I'll put that here. So that's my expression for relative error. Now, if you notice, this expression for relative error is based on the difference between these consecutive estimates, xi plus 1 minus xi. All right. So after I have the first iteration, I really don't have any idea of the accuracy of my approximation. So I'm going to void this out. Whoops, just going to delete that. At this point, my best estimate for the accuracy of my approximation based on the data I already have is the difference between my previous estimate and my current estimate. So I'm going to take the absolute value of the difference between my previous estimate and my current estimate. Right? In fact, this estimate is much more accurate than this. The error is only about 0.03, but this is a upper bound for the possible error. So if I fill this down, I'm going to get maximum error. Edit, fill, down. Okay. And we can see very small errors. All right. These are absolute errors. If I want to do relative errors, I can also do that. I could say max relative error and actual relative error. The relative error is obtained by taking the error which is in this column here. This is empty, but I don't care. When I fill down, it will give me the correct value anyway. And I'm going to need a parenthesis, so I'm going to click in here and put a parenthesis. No, I'm sorry, I'm not going to need a parenthesis. That's just fine the way it is. It's the actual error divided by the value that I've obtained times 100 for a percentage. So let me fill this down. So here we see 29% error. The error rapidly goes to very close to 0%. And here, if we want the actual relative error, we'll take equal to this error divided by, in this case, it's going to be the true value times 100. Okay, and we'll fill this down. Okay. I'm sorry, I have to fix the reference for the true value again. Let me click in here. This B6 should be fixed when I take the true value. So that's Shift F4. Okay, so you can see the formula here. The actual error divided by the true value times 100. Let's go ahead and fill this down again. Okay, and now we're looking good. Okay, notice that the actual relative error is the actual relative error is also always smaller than the maximum relative error. The maximum relative error is about the same size as the actual relative error for the previous iteration. Let's compare these two again as we did before. Okay, and we'll take a graph. I want a line chart. I want points and lines. And the data series is correct. Max relative error, actual relative error. My x-axis is going to be iteration number. And my y-axis is going to be error, a relative error. Okay. Let's finish it off. Okay. This 0 here is an artifact because I don't actually have an estimate of the error at the beginning. I'll fix that in a minute. But I do want to change the y-axis here to a log scale because that will make it more clear. So I'm going to go here until I see y-axis. Then I'll right-click, Format Axis, Logos Scale. Okay. And we can see that The logs plummet almost immediately. Okay, they just plummet down to values too small even to record. Okay. Let me move this graph to a place that's convenient. So I'm going to click in the spreadsheet once, click back on the graph, right click, cut, move. I'm going to move the graph up here. I'll move it here. Right click, paste. And let me make the graph a little bit smaller. I'm going to have to go over here and grab this green square, move the green square up. Okay. And you can see the values here. Now, as I said, I really should take this relative error here away because it's not a true value. So here we have the iteration number. Now, I could change this graph if I wanted to start with a different initial guess. Let's say I start with the initial guess of 3. Okay. Notice that when I do 3, I'm getting errors here. I'm getting very large errors. Let's see why. The x it found was actually not 1.5707, but this value minus 4.71. Now, if you work this out, this is actually a root of cosine. So there's no problem here. It's correct. It just converged to a different root. All right, so you can see what can happen with the Newton's method.